This is the video on the fourth side of a triangle, of every triangle, and why that is even a thing that we talk about, that I talk about. Gonna make it a laid back explanation, not gonna get too into the weeds. My cat's meowing at my window. It's gonna be something that I hope is easy to grasp, and we're just gonna run through it. I'm not gonna try and do any retakes of this. So, why do we even have it as a concept? Why is it even a question whether or not triangles have four sides, or three sides, or four, whatever? It all starts because mathematicians love defining things. They really love maths because it's a self-sufficient and internally consistent system where if you can make things make sense within that system and prove themselves within that system and all work together, then you know that you can apply that. And maths will always work because it's designed to work with itself and form patterns and be reducible and deducible. Defining things is cool. And more importantly, if you can define something really basic, like really fundamental, that's pretty cool as well. If you can get to them axioms and like do a proof for those, that's great. When I say axioms, I mean literally writing a 300-page proof for 1 plus 1 is 2, which is a thing that exists. I don't know how to talk about it anyway whatsoever, so I'll talk about this instead. How do you prove or show or define what a triangle is? There is an easy way. There's an easy answer, which is, oh, we have three vertices. If you connect them, you literally can't fuck up connecting them, and you make a triangle. But that's like the, duh, of course 1 plus 1 is 2. That's just how it is version of that argument. Mathematicians want a really rigorous and well-defined and internally consistent explanation that you don't need to rely on anything else for. Turns out, triangles and circles got a lot involved, and you can define triangles with their relationship to certain circles. For this conversation and explanation, we're going to be looking at a way of defining a triangle using three circles. And we're looking at this one because it has a small hole in it that means that you can fit a fourth side in, which is fun. We'll get to that. But for this definition, the way it works is there are three rules. And they refer to the ways the edges of the triangles, these bits here, interact with those circles. So rule number one, each side has its endpoints on the circumcircle. We're just going to blast through these and then explain them afterwards. Number two, each side touches the incircle. Rule number three, each side has its midpoint on the 9-point circle. If a side, or if a line, satisfies all three of these rules, then you can, this proof states that it is, then that line segment is a section of this triangle, or is a side of this triangle. And it's pretty elegant, and it works really well. We're going to explain how it works, and then explain the flaw in it. So, let's go through the rules one by one. Each side has its endpoint on the circumcircle. Now, what is a circumcircle? It is this. It is a circle that is that touches all three vertices basically. So you can see that each side, side AC, which is the line going from A to C, side AC has its endpoints on the circumcircle. AB does as well, and BC does as well. So each line ends at the circumcircle. Second rule, each side touches the incircle. What is an incircle? It looks like this. And it's also fairly simple. It's the circle made when you try and just fit the biggest circle that you can inside of a triangle. There's only one. You get to a size, and that's the incircle. It's the one that perfectly touches each edge at one point, and it's as big as it can get. That is your incircle. These two circles are pretty cool to understand. It's just like the one that touches all the vertices, the one that touches the edges. The third rule is not quite as simple. Each side has its midpoint on the 9-point circle. 9-point circle. Incircles are easy, circumcircles are easy. What is even a 9-point circle? It's this. And more specifically, it's this. Just before we tackle this, let's refresh. Each side, has its endpoints on the circumcircle. Each side touches the incircle. Cool. Our triangles following these rules so far. Each side has its midpoint on the 9-point circle. I'm going to go through what the 9-point circle is and explain it very simply, but just know that it's a circle that has to be it is a specific way, and this triangle interacts with it, and it works. We're going to do it very briefly. Hold your horses, you're going to be okay. This is the 9-point circle. Don't worry about anything on this except for these circles here. These are the 9 points, and they're fairly simple. These 3 points here are the midpoints. I drew that awfully. And the midpoints of each line segment, or each edge, I should say. That's all these 3 points are. These red points, just the midpoints of each edge. That's fine. These blue ones are the foot of each altitude. Fancy way of saying, hey, if I draw a line from this vertice, or this edge, to the bottom here, and I want it to be perpendicular, I want that line to interact, or make a right angle with that triangle, this bit here. Oh, that's gross. If I wanted to do that, where will that land? So you start at the vertice here, you draw a line that hits this at a right angle, and that's your foot of each altitude. That's the altitude, here's the foot. Boom. So we got midpoints of each edge, foot of each altitude. The last 3 points on a 9-point circle are the Euler points, or more simply described as the midpoint between the vertice and the orthogonal center. The cat is rummaging at the door. No, I'm sorry. Listen, I love you. I'm nerding out right now, and I can't have you as a distraction as much as I love giving you pets. I really can't. Euler points. Basically, when you've got the foot of each altitude, it makes a line. Each altitude is a line. Where they connect, this is called the orthocenter. You can find the midpoint between any of these vertices and that point there. Here they are. It's just the middle point between this bit and this bit. And it's the same for all of the vertices. Oh my god, come on the chips. Yeah, come on, yeah. That is it. That's all you need to know. So just to recap, the 9-point circle, this is the third circle that's important to our triangle. The only thing you need to know about it is where these points are. You don't even really need to know that. I'm just explaining this, and you can replay this if you were interested in understanding it better. But it just goes to these points, and they're important for a triangle. So we'll add our 9-point circle. That's this one here. We've got our 3 circles, and we know how they should interact with our edges. That's fantastic. Yippee. They all appear to be doing that. That's great. We know that these edges, these line segments, fit the definition because they interact with all of these circles in the way that it should. Has endpoints on circumcircle, touches the incircle, and the midpoint of each line is on the 9-point circle. There's one more line that does this. And here it is. That is a line that has each side of its endpoints on the circumference that touches the in circle. I made them both red, that's not great. And has its midpoint on the circumcircle. It is wacky that that exists, and it's really fun. But it's just a cool, interesting hole in this proof, or this definition. The reason I've been talking about it so much is that I've drawn one. And it is a hard feat, let me tell you that. To draw one that's like vaguely mathematically accurate and to scale, accounting for inaccuracies that anyone has while drawing with compass and ruler. The reason it's hard to draw this is basically just doing the 9-point circle, and the in circle is quite hard. You can draw a big circle to start with and then just choose 3 points on it, and you've kind of cheated and found the circumcircle by just making a triangle inside of it. Boom, 1 circle done. The in circle, this one here, is kind of hard because you've got to like find where it perfectly touches it and find the exact center. The 9-point circle, doing all this shit is really fucking hard. And I tried to do it algebraically. I tried to do it mathematically. So I pretended that my piece of paper was a grid like this, and I measured the distance between the points, and I plotted them, and I did the maths for them. The maths looks like this, by the way. the maths looks like this. The maths looks like this. And I didn't do the maths right, funnily enough. I wasn't quite up to scratch. But then I found out you can do something called a compass and straight edge reconstruction, or construction, which is basically a very clever way of using no measurements and no like marked rulers or anything, or whatever, just a compass and a straight edge to make this. It's really interesting. And if I make my camera big, oh my god, come on. There we go, and I tilt it down. Looky what we've got right here. First of all, it's a baby. It's a little guy. This is my Sherman line. And I hope you notice the similarities. Oh my god, the baby is so curious. Jesus Christ. Oh, don't step on my keyboard. Thank you. This is my Sherman line. Okay, she's gone. We've got our circumcircle. We've got our in circle, and we've got our 9-point circle. And the next few pages are basically the proofs or the instructions for how to do this, and how you do like ruler and compass constructions. So this is a great example of finding a midpoint of a line. Whoa. It's actually a really badly done example. Yeah, actually, we're not going to use that one. We're going to use this one. So you can. Oh, no. I'm actually not going to try and explain these compass and ruler constructions. They're hard. That's not anything to do with that. But yeah, here's that. Oh, and fun fact before, here's the pages and pages of the maths I tried to do and failed at. Oh, agony. That's actually only 2 pages. I stopped when I realized I was not doing well. But yeah, basically you can find things like midpoints and orthocenters and copy angles and draw circles and whatever with just a compass and a straight edge. And I did that. And it is so fucking cool that I did that. That's literally it. I wanted to share that. Just that I managed to make this shape with pretty good mathematical accuracy and construct a Sherman line, which is just sick, I think, personally. But yeah. Glad I didn't do all the fucking horrendously difficult maths. I'm glad I didn't continue the mathematical route, because this it's not good. But yeah, that is the Sherman line. That's how triangles can have four sides, but not really because it's just a flaw in a definition that's super niche. But I made one, and I'm very proud of that because it was really difficult. That's all.